Hello, my name is Yagudin Rustem. My academic advisor, Professor Mikhail Verkhaturov. Recently, I have successfully finished my postgraduate studying in Ufa State Aviation Technical University. Now, let me present you my finest results in the thesis One Approach for Solving the Non-Convex Polyhedrons Dense Packing Problem based on Dynamic Usage of No-Fit Polyhedron. Currently, there is a lot of scientists involved in research of this kind of 3D packing problems. But there still exists some open questions because those problems are significantly different from each other. Let's consider 3D packing problems. Of course, there is a classic beam packing problem about packing parallelepiped objects into parallelepiped containers. Also assembling problem about finding most mutually beneficial arrangement. Also diamond cutting problem and even a kind of decorative paving problem. In addition, a most complex and intensively investigated today the problem of additive manufacturing processes optimization. Additive manufacturing based on growing three-dimensional objects layer by layer. Since 8D machines are very expensive and produce objects very slow, it's necessary to produce as much details at the same time as it possible. Next slide propose cutting and packing problem classification. Therefore, I will consider a single production of 3D non-convex objects with a single packing area. Now you can see the problem formulation. There is given a set of polyhedrons and a packing area that have fixed base and variable height. Each polyhedron have its placement parameter, which describes location of polyhedron inside the packing area. Of course, there exists not overlapping conditions between polyhedrons, as well as the fact that polyhedrons must be inside the packing area. The objective is to find placement parameters that minimizes the height of the packing area. To solve described problem, I have used a heuristic method based on satisfaction the non-intersection conditions using a no-fit polyhedron. The solution structure consists of two parts. There is one simple idea behind that. If we will get determinate method of placing polyhedron into a packing area, then the result will depend only on packing sequence. That's why it's possible to separate the optimization component from the geometric one. The objective of optimization component is first, generate start packing sequence, second, modification of the previous packing sequence based on packing result analysis in order to improve solution. The objective of geometric component is first, providing fulfilling of non-intersection conditions, and second, determination of placing parameters according to input placing sequence. Let's consider geometric component first. The most advanced tool that can help to fulfill non-intersection conditions is a no-fit polyhedron. If we'll get polyhedron T1 to be fixed and T2 to be movable, then NFP is a locus of the reference point of polyhedron T2, whereby T1 and T2 intersect by their frontier points and have no any mutual interior points. On the bottom of the current slide, you can see one example of NFP building for two-dimensional case and two for three-dimensional case. For two-dimensional case, I have tried to make animated example. As you can see, green movable rectangle travel along fixed blue object in such a way that their frontier black borders are always connected, but objects never intersect by their interior points. At the same time, the reference point of movable rectangle builds NFP. That way, NFP may be considered as a border of the zone permitted to place movable object. For dense packing, it's important that objects touch each other as well. Okay, now we know what is NFP, but how to use it to pack objects. Basically, there's two ways to do it. One of those, let me call it preliminary, based on idea that NFPs of each polyhedrons pair between each other and the packing area are built before packing phase start. On the left picture you can see small triangle to be packed. And there is already built 3 NFPs. One to the packing area and 2 of those to already placed objects. Placement parameter coincides with the lowest concavity vertex. Second scheme, based on idea that NFP of polyhedron to be packed and the packing area are built with taking into account the fact that all previously packed polyhedrons considered to be part of packing area. On middle picture you can see that border of area permitted to place objects consists 3 connected separated parts. First part, second part, and last one, big part. Here, 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 and here. Third scheme disadvantage is that in many cases it causes building of abundant NFPs, and second scheme simply may not be applied to three-dimensional case, because in three-dimensional case there is no separated parts appear in common case. That's why I have proposed a new dynamic scheme. It modifies preliminary one by restricting of abundant NFPs built. Here is dynamic scheme features on example. Let to be placed first m-1 polyhedrons of the set T, and Tm should be placed next. First feature is that NFP built sequentially according to priority list K. First object in this list is a packing area, and others are already packed polyhedrons sorted by ascending their placing height. Second feature, once next NFP according to priority list K built, all placement parameters belong to it are checked for permissibility. The placement parameter may appear on concavity vertex or on intersection with the border of other NFPs. For this example, we have built NFP for objects K3 and found placement parameter on intersection with NFP to object K2. The placement parameter permitted if it doesn't belong to the inner of all other NFPs, which may be constructed on current packing step. It's obvious that if parallelepiped hulls of polyhedron Tm placed according to found point and polyhedron Kg do not intersect, then the fact that placement parameter do not belong to NFP to Kg may be guaranteed without building of NFP to Kg. The final feature, if there is found permitted placement parameter, then there is no reason to build NFP for already placed objects whose minimum Z point higher than maximum Z point of polyhedron Tm placed according to found permitted placement parameter. The reason is that our determinative method aimed to finding of lowest permitted placement parameter. All placement parameters may be found by considering of concavity vertices of the union of constructed NFPs. On the current slide, proposed an example of 3 polyhedrons packing. At the first step, there is no NFPs to be constructed, except the NFP to the packing area, and the placement parameter coincides with the concavity vertex here. On lower picture, you can see first object placed according to found point. On the next picture, placement parameter coincides with the intersection point of concavity edge of NFP to placed object and the face of the NFP to the packing area. And here, second object placed according to found point. On the last step, the placement parameter coincides with the intersection of 3 faces of 3 different NFPs, 2 for already placed objects and 1 to the packing area. And on the lower picture you can see third object placed according to found placement parameter. Now we know what is NFP and how it can help to pack polyhedrons. But how to build it? Let me introduce a new NFP building method. It's based on construction of pseudofaces. That term was introduced by Chernomorets. Pseudofaces construction for a two-dimensional case are shown on the left picture. To construct them, it's necessary to consider all cases of objects' contact. As you can see, there is a lot of abundant components, but pseudofaces contains all points of desired NFP. Chernomorets propose a method to remove all abundant components from pseudofaces and get clear NFP. You can see clear NFP on the middle picture. However, I propose to find just outer hull of pseudofaces, which is equal to outer hull of NFP. It's totally useless to deal with two-dimensional case, but if use it on three-dimensional case, we will kill 2 birds with 1 stone. Inner parts of NFP described disposition of one polyhedron inside another. However, the manufacturing details, according to that model, may not be separated from each other. On the other hand, reducing amount of NFP fragments will significantly reduce the calculation time. NFP building is the most complicated part of my work. So, let me start from detailed example. Here is the 2 already familiar polyhedrons. First one and second one. Let's consider this one to be fixed and another one to be movable. As I have said, we need to consider all contact variants of polyhedrons. Let's do this. First contact variant is touching of one face of one polyhedron to another face of another polyhedron. Second one is touching edge of one polyhedron to the face of another. Now it's touches of 2 edges. And last one, touch vertex and face. As you can see, travel point, draw the slide path. After consideration of each contact, we receive a pseudophase of NFP. For phase vertex case, it's a simply phase shifted by a vector. Let me show you. Here it is. And travel line belongs to it as well. So let's return back and consider edge-edge touch. And it will be a parallelogram whose sides built on considered edges. This edge here and this edge here. For face edge and face touch cases, NFP parts will be equal to NFP of two-dimensional components. Here is this component is edge and face of fixed object, and let me show you what will happen. It's NFP of this face and edge shifted by a vector. And let's go a little bit more back, and this component is NFP of two faces. First face this of fixed component and face of movable one, and here is NFP. Building of two-dimensional NFP is a separate problem, and I will not consider it at my presentation, but I can tell that face and face edge cases are very rare on common NFP build case. So maybe I forget to tell you that this black point is a reference point of movable object, and this line is a travel path of origin or reference point, whatever say. If during polyhedrons contact there exists separate plane which is divide polyhedrons from each other, then pseudophase will totally outer and completely belong to outer hull of NFP. That face is colored as green, and here is green face when touch these faces. Here is separate plane, and here is also exists separate plane, and here exists separate plane, but here it is not. You see, here if we'll make plane through that face, then it will intersect another face. Otherwise it can be confirmed that face outer, and that face colored as red. That way only red faces may contain abundant components. Now let me travel a little bit more. Here we are. Now you can see the full set of pseudo edges. When movable object slide over the fixed one, travel line will always belong to our pseudo faces, which is proof that pseudo faces contains all points of NFP. Now it's possible to recursively bypass pseudofaces from outside. This bypass starts from definitely outer green pseudofaces and grabs red faces fully, for example this fully grabs, or partially, for example these intersected red faces. The union of fully or partially bypassed pseudofaces is exactly equal to desired outer hull of NFP. Here it is. In the cutted places, here, appear concavity edges, which can be used to find placement parameters. Let's consolidate everything we get. To construct desired outer hull, it's necessary to find pseudofaces. On the picture proposed all contact variants of polyhedrons. It's face-face, face-edge, face-vertex, and edge-edge. After that, we may determine which of faces are definitely belong to the outer hull of pseudofaces, object S. After that, recursively bypass object S from the outside. This bypass starts from definitely outer pseudofaces and grabs other faces fully or partially. The union of bypassed parts of object S is equal to desired outer hull of NFP. That's it. To generate and change placing sequence, I have used two methods. First, fit with sorting, based on sorting polyhedrons according to decrease in their size. That way, big objects placed firstly, and after them, small objects to be placed. Second method I have used is a greedy, randomized, adaptive search procedure. It's based on balancing between greedy and random elements, and give pretty good results. Both methods, first fit and grasp, used local search to increase the quality of solution. Experimental calculations was performed on two sets of input data. First one consists of 4 problems. It was presented in a paper given by Yuri Stoyan and Guntram Scheithauer in 2004. Smart Space is a packing component of Magix software developed by Materialize company. Is also have used to compare the quality of packing. Results shown that for first two problems, best solution obtained using grasp plus local search method. For last two, best solution obtained using first fit plus local search method. Utilization of best found solutions are also given. Now let's consider how objects placed inside a packing area for best example for fourth problem consists of 50 objects. Now let's put objects sequentially one by one and show how are they placed inside a packing area. First object placed, another one, another one. This is box with hole. Another one, another one. This is here. Here another. Here it is. That's pretty cool. to be honest. And here this I don't know how to say, maybe window, it's pretty cool placed. Next one, fourth, next, another window. You can see this object go through, but do not intersect it, of course, because our NFP works perfectly. Here is another one object, it placed inside the box, but of course without intersection. Here another box, another one. This is here. Here in the box another object. This is out of box. It cannot be placed here because this object restricted, and it placed here. You see? Now next, and now the smaller ones will go. Here it is, small object placed inside a box. Here it is. Here another one, another, and another one. You see, it's pretty cool. Another, and there's 4 left more. They are placed here, and last one here. So this looks pretty good, I believe. That's how it works. NFP works perfectly. It restricts placing objects with intersections, and find the lowest point of placing for current ready to go object. Another set of input data contains 5 problems. It was presented in a paper given by Jens Egblad at 2009. Results shown that for first 4 problems, best solution obtained using grasp plus local search method. For last one, best solution obtained using first fit plus local search method. Visualizations of best found solutions are also given. Thank you for attention. I have shown you my finest results. I believe my work will help someone to find his own path. If you have any questions, you can write it below or send me to email. Thank you again.